Alrighty, so we're going to continue along with optics. Last time, or in the past, we talked about polarization. And we found the big equation for polarization was called law of Malus, and it said the intensity of light, which makes it through a polarizer, is given by the original intensity of that light times the square of the cosine of the angle between the initial light's polarization and the polarizer's angle. Then we discussed refraction, the bending of light as it goes from one medium to another, and that gave us Snell's law, which was n1 sine theta 1 is n2 sine theta 2, where n, of course, is the index of refraction for the material. And then with this, we also discussed critical angle, which was the special case of refraction, where if you go from a more dense medium to a less dense medium, so a big index of refraction to a small index of refraction, then there's the possibility that the light will not escape the medium, but will just skim the surface. And the angle of incidence, which allows this to happen, is called the critical angle. Well, today, we are going to discuss what's called ray optics. And just as the name implies, this is how light rays work. And so this is going to talk about lenses and mirrors and things like this. How do lenses and mirrors change the path of light, focus light, these kinds of things. Now we're going to do this in two ways. We're going to do this by what's called ray tracing, which is a graphical method of solving problems. And then, of course, we're going to do this analytically, which means we're going to do it by equations. And we're going to find that we get, if we're accurate, exact same results for the two methods. And if we're a little inaccurate with our drawing, then at least they're similar. So, first thing we're going to discuss is mirrors. Of course, we know how mirrors work. If you have, let's say, what's called a plane mirror. So here's my mirror. And there's some light here. Well, the light sends off a light ray off. Of course, it travels in a straight line to the mirror. When it hits the mirror, what a mirror does is it reflects the light. And so, of course, we're going to have the light ray coming off the mirror, but we want to know exactly where does this light ray go. It turns out that the law of reflection says if you draw the normal line, that is the line perpendicular to the surface of the mirror, where the light ray hits the mirror, then the reflected ray will come off the mirror in such a way that the angle of incidence, call it theta I, is equal to the angle of reflection, theta R. So angle of incidence is angle of reflection. Light ray comes in, it goes out at the same angle. Basic stuff. We're used to it. We see it all the time in our daily lives. However, what's a little more interesting is what if we have a mirror that's not a flat plane mirror, but is curved, a curved mirror called a spherical mirror. Then I want to know, how does light react with this type of mirror? So let's say we have a mirror that looks like this. This is called concave. Because if you think about light coming in from the left, it sees like a caving in type surface. So concave, that's how I remember it. Concave is where the mirror kind of comes into itself. So the question is, if I have light, some object at a certain location away from this mirror, how will the light rays react? So the first thing you do is you have to understand things about the mirror. There's certain characteristics we need to understand about this. First, there's something called the focal point of the mirror. Now, the focal point of a mirror is found like this. If we have a mirror like this, and we have a bunch of light rays coming in from very, very far away, so all the light rays are coming in parallel to themselves, then what will happen when those light rays hit the surface is all of those light rays will reflect off. How will they reflect off? Exactly the same way as for the plane mirror. If you take a look at this top ray, I have to make a little normal line at the surface, and a reflected ray will come off at the same angle. And so I would do that for every single one of these. Make a little normal line at the surface. And what you'll find is all of the rays will tend to reflect back. That one was a little poor, but they'll all reflect back such that they go through the same point. So if I drew this accurately, every one of these rays coming in, when they reflect, they all pass this single point right here. That point is called the focal point. Now, depending on how curvy the mirror is, the focal point will be at different locations. So, if we know the focal point of the mirror, that tells us something about how curvy the mirror is. For instance, if I have a very curved mirror like this, then the focal point will be very close, but if I have a very shallow mirror like this, the focal point may be very far away. So the distance from the mirror to the focal point is called f naught, or just f if you want, and it's called the focal length. So you can measure it, of course, 10 centimeters, 25 centimeters, whatever it happens to be. The focal length is the distance from the mirror to the focal point, and it's an important piece of information because it tells you how curved the mirror is. So, starting back at the top with our spherical mirror here, first thing we want to do is draw in what's called, we draw in the focal point, of course. Let's say the focal point happens to be right here. Next thing we're going to do is draw what's called the principal axis. And a principal axis is just a line, horizontal line, that goes straight through the focal point and through the center of the mirror. So that line right there is just called the principal axis. And then, of course, the last thing we draw is the object. Now, the object that will be sending the light rays could be anything. It could be a person, it could be a light bulb, it could be the sun, whatever it is. The way we're going to represent the object is by an arrow pointing upwards. This helps us later on when we discuss what type of image we're going to have, whether the image flips or not. And so, if, for instance, we have the focal point there, the green dot, let's say we have an object here. Here's our object. All right, now what I have to do is I need to draw the rays of light emerging from this object going towards the mirror. They're going to reflect off the mirror, and then where these light rays cross, that's going to be the focus where the image is located. Now, don't confuse that with the focal point. Remember, the focal point was the point where all parallel rays emerge. In this case, we're going to have our object, and the object, if you look down here, the light just comes off in all directions, all emerging from this single point. So, The reason I said when I was discussing the focal point, the object was very far away, so the light rays are parallel, is because if you see for this object down here, the light rays are coming off all at different angles. They're not parallel, so when the light rays emerge from an object for a mirror like this, fairly close, they're not going to cross at the focal point. The focal point is just there to help guide us on what to do, but where the image is formed is going to be somewhere totally different, and that's what we're trying to find. Now here's the thing. There are three rays that we can draw because we know exactly how those rays will work. There's an infinite number of rays actually coming from the object, but three of them are very important because three of them we know something about. So I'm going to draw them. The first one I'll draw, let's say, in red. So this ray is a ray that starts at the object, and it's going to move along towards the mirror parallel to the principal axis. So here it is, moving parallel, then it's going to hit the mirror. And now I know this ray is going to reflect, and I know just looking at the system, it's going to reflect downwards somehow, but I need to know exactly where downwards it's going to reflect. And I don't feel like having to draw these normal lines over again. The reason this is a special ray is because I know if the ray was that ray which goes parallel to the principal axis, then when it reflects, it always moves through the focal point. So that's how our first ray goes. It starts at the object, moves parallel to the principal axis to the mirror. Then when it reflects off the mirror, it reflects off in such a way as to pass through the focal point. All right, the next ray I need to draw, again, starts at the object, and this time the one I'm going to draw goes from the object through the focal point to the mirror. So we start here, it goes through this focal point to the mirror, straight line, and then when it reflects off, the way this thing reflects is the exact opposite. Now it's going to reflect back parallel to the principal axis, like that. So these two lines are kind of opposites of each other. The red line starts parallel to the principal axis, then reflects through the focal point. The blue line starts through the focal point, and then when it reflects, it goes parallel to the principal axis. Now, I already know where these two lines cross, right here. I draw a little arrow from the principal axis down to there, and that is the image. So I already know my answer. I would get out a ruler, I would measure the distance from the mirror to this new gray arrow, and I'd say, okay, the image is such and such distance away. I can look at the arrow, it's upside down now, so that tells me the image is inverted. I can look at the size of the arrow relative to the original size of the object arrow I drew, and that'll tell me if the image is magnified or smaller. So I get a whole bunch of information. I've already solved the problem. But there is a third line I can draw. And I'll show you the third line because sometimes it's important to know this one too. The third line is going to be a line that starts at the object. It's going to hit the center of the mirror where the principal axis is. So let's try to draw this. And then that's going to reflect off. And the way this reflects is just the same as our original mirror. The angle of incidence is the angle of reflection. So when it reflects off, it's going to reflect off at the same angle that it came in at. And of course, it has to cross where the other two crossed, because that's where the image is. So this yellow line, the angle of incidence, that is this angle it makes with the principal axis, is the same as the angle it makes with the principal axis on reflection. So that's how you know how the yellow one will be drawn. So those are our three main rays. The red one, parallel to the principal axis, then through the focal point. The yellow one, from the object to the point where the principal axis and the mirror cross. And then when it reflects at the same angle. And then finally the blue, through the focal point to the mirror, and then when it reflects, it's parallel to the principal axis. Where those lines cross, that's where your image is located. And again, what we want to know is, number one, where is the image? That's called the image distance. But we want to know more than that. Another thing we can know is this image real or virtual? And I'll discuss what that means. Number three, is the image inverted or upright? And four, is the image magnified or minimized? So every problem you do with ray optics, you can answer these four questions. Whether you're doing this by ray tracing, like I just showed you, or you do this analytically, there's going to be ways of figuring this out. So for the first question, let's look back at it. Where is the image located? Well, of course, just to put some notations here, first of all, the distance from the object to the mirror, that distance is called DO, or the object distance. So if I say in the question, you have a mirror whose focal length is 10 centimeters, the object is located at 25 centimeters away, that means the object distance is 25 centimeters. The distance from the mirror to the object, that's 25 centimeters. The distance from the mirror to the image, of course, that's DI, or the image distance. So where will the image be formed? That's called the image distance. So looking at this, I would get out my ruler, I'd measure from the mirror to the gray arrow some number, that's called the image distance, so I know the image distance. Second question, is this image real or virtual? It turns out, as we will see with some examples, the image can be formed either like this one on the left side of the mirror, but also the image can be formed on the right side of the mirror. So to figure out if this is real or virtual, it turns out if the image is located on the same side as the object, then it's real. So if the object was on the left side of the mirror, you do your ray tracing and your image arrow is also on the left side, it's a real image. Virtual image is if the image is on the opposite side. Now again, we're talking about mirrors. It turns out for lenses it's the opposite. But for mirrors, if in this case, for instance, this gray arrow is on the left side of the mirror, the black arrow, which was the object, is on the left side, they're on the same side, this is a real image. If the arrow was over here on the right side, then it would be a virtual image. All right, number three, is the image inverted or upright? Well, that's easy. You look at your image arrow. You know your original object was the arrow up. If your image arrow is also up, then it's upright. However, in this case, our image is downwards, so I know my image has inverted. So that's how you know if it's inverted or upright. Very easy. You look at the image arrow. Is it going from the principal axis downwards? Then it's an inverted image. If it's from the principal axis upwards, then it's an upright image. And then lastly, is the image magnified or minimized? Again, you look at your two arrows. When you draw these arrows, of course, you're going to be as accurate as you can. So when you get out your ruler, you'd measure, okay, well, how big, for instance, is this object arrow? I would call that HO, the object height. Now, I hate this term, object height, because it makes you think that it's something above the ground, some height above the ground. But it's not. What they mean when they say object height is the size of the object. It's 20 centimeters, or it's 10 centimeters tall, or whatever. And of course, the size of the gray arrow, that's called HI, which is the image height. So how tall is the image? If the image is taller than the object, then it's magnified. The image is bigger than the original object was. However, if the image is smaller than the original object, it's minimized. So, very easy to figure out these 4 questions. The key, of course, is can I draw these situations, this ray tracing, accurately? So let me give another example. This one's important. What if I have a different type of mirror? This time I'm going to do a convex mirror. So here's my convex mirror. Here's my principal axis. And I'll say, okay, here's the focal point. Notice the focal point's on the right side this time because the curvature of my mirror is to the right. So of course, the focal point has to be to the right as well. Now I'll place my object. Let's say my object goes right here. There's my object. So this might be, focal point is 10 centimeters, and the object distance here might be, let's say 20 centimeters, and I want to know what's the image. So again, I do my little arrows, or my rays. The first ray always starts at the object, parallel to the principal axis to the mirror. Now, what is going to happen? Well, obviously, I know just by looking at the curvature that my ray is going to reflect upwards. But how exactly does it reflect upwards? Very vertically, kind of horizontally. It turns out that it's going to reflect upwards such that if I extend the line backwards, it'll go through this focal point. So that dotted line there is fake. It's not a real line. That's not what the light's actually doing. But it's a guide because it shows me, it shows me how the ray will go. It'll go like that. So what's really going on is the solid line. The solid line is what this light ray does. However, in order to draw it, I had to draw this dashed line on the right as a guide to show me which way it's going to go. So very similar rule as before. You start parallel, and then the line goes through the focal point. However, in this case, obviously, the light can't get to this part of the mirror. This side of the mirror is blocked. It's a solid mirror. All the light has to reflect to the left. So that's why the light doesn't actually go through to the right. It goes to the left like it should, but this fake line helps me figure out how. Now for this one, this is why I had to show that third line, because it turns out I can't do the line that goes from the object through the focal point to the mirror because the focal point's on the wrong side. But I can do the third line, and that line was the one that went from the object to the center of the mirror, and then when it reflects off at that same angle that it came in at. This angle is the same as that angle, and so that's what the blue line does. Now notice something. The red line and the blue line never cross. On the left side, where all the light exists, those two lines are actually diverging. So this is called a diverging mirror. Because the light rays, after they reflect, diverge from each other. They never converge. So the other mirror you can call a converging mirror. They never converge, so that means they never give rise to a real image. The image can only be made when those light rays cross. So, first big thing, not a real image. However, what we can do is manipulate something. Let's take this blue ray that reflected off and let's extend him backwards as well. And now what I see, where these two fake lines converge, I could draw a little arrow there. That is where my image is located. Obviously, this is not a real image because no light is on that side of the mirror. However, this is called a virtual image. Okay, that's fine. So we have a virtual image. Where is it located? I get my little ruler out. I measure that distance. It looks like it's about 5 centimeters away if the original focal point was 10. Is it upright or inverted? Well, look at the arrow. The gray arrow is upwards, so it's an upright image. Is it magnified or minimized? Well, just looking at it, the gray arrow looks smaller than the black arrow. The gray is the image, the black was the original object. If the image is smaller, then it's minimized. So this is a virtual image, upright, and it's minimized. And of course, I would measure the distance. Maybe the image distance is about 5 centimeters or something. But notice, convex mirror, we have to do different than we did the concave mirror. But if we follow our rules, it's not that complicated. Let's look back at the original mirror, the concave mirror. The first ray was this red ray. It starts parallel from the object, it hits the mirror, and then when it reflects through the focal point. Another ray is this yellow one. The yellow one goes from the object to the center of the mirror, where that principal axis is. And then when it reflects off at the same angle that it came in at. The last ray is the blue one. It goes from the object through the focal point to the mirror. And then when it reflects parallel again. Where those lines cross, that's where my image is located. Now for the convex, same thing. The red line starts parallel from the object to the mirror. And then when it reflects, what goes through the focal point is the fake dashed line going backwards. I have to make it dashed because no true real light can go through a mirror. A mirror is solid. So it's fake lines that go back there, but it helps guide me to figure out how my light ray will reflect off. Then my blue line here, that's like the yellow line before, it's exactly the same. It goes from the object to the center of the mirror, and then when it reflects at the same angle. The other line I couldn't draw in this case because there's no focal point on the left. So I can only have two, but that's all right. As long as I have two lines that cross, I know where the image is. So how do they cross? Well, I have to extend all my lines backwards. The red one was already extended for me. In this case, I had to extend my blue line backwards. And where the two lines cross on the back, that's where my little virtual image is located. Now, we're going to discuss lenses as well, probably on the next video. But I did want to leave you with one problem to try yourself. What happens if I start with a mirror? Let's say it's a concave mirror. Here's my focal point. Let's say I start with the object inside the focal point, like this. There's my object. Try to recreate this and try to see if you could find out how the image goes. On the next video, I'll do it myself and I show you what's up with this one.